Good morning, good afternoon, everyone. It's 10 o'clock here in the Netherlands. We're going to start. Welcome to today's Energy Tech Talks. My name is Eric Neyveld, CEO and co-founder of technologycatalog.com. I'm your host today. Today's webinar is organized together with ROSEN, a company that helps customers to realize the full potential of their assets. Richard Veuken will be presenting on tank bottom inspection. Ronald Tuls will provide insights and experiences about corrosion on the pipe supports. And Louis Barton will present on inspection of unpickable pipelines. If you have any questions, please type them in the Q&A box that you'll find on the left-hand side of the screen. Please indicate for which presenter the question is. Following each presentation, we will cover one or two questions, and we will do a Q&A session at the end with all three presenters. In case there's time left at the end, I will also give a brief update about technologycatalog.com. So with that, I would like to hand over to Richard.
Eric, thank you very much for the introduction. And I will start my presentation. Welcome also from my side. My name is Richard Veuken. I'm working as head of NDT products and applications in the ROSEN Technology and Research Center in Lingen, Germany. And before I will talk about the tank bottom inspection with T-Bit Ultra, I will spend a couple of words to introduce also what ROSEN is doing. And after my presentation with the T-Bit, my colleagues will take over to talk about the CAPS inspection as well as the NIPA inspection. So what is ROSEN doing? So our core business is of course the inline inspection of pipelines. That's what our main business is. However, we are also active in a lot of other fields, like for example the non-destructive testing, the business line where also Ronald, Louis, and I am located, and I will talk in a minute also a bit more in detail what is all under this business line. But we are also offering all kinds of integrity assessments on different assets, on tanks, on pressure vessels, on piping and pipeline. And next to it, we're offering cleaning services, mainly pipeline cleaning services as preparation of intelligent ILI runs. And this is all accompanied with also software solutions in the course of asset integrity management, like NEMA, but also reporting software like ROSEN for tanks is something we can provide our customers with. And last but not least, we also support our customers with technical expertise and consultancy services also around the asset integrity management. The NDT service portfolio at a glance. So as I mentioned, Ronald, Louis, and I are working in a so-called business line NDT Diagnostics, and in that business line we are dealing with the inspection of storage tanks, for example with the T-Bit Ultra, where I will talk about in a minute. But also we offer complete inspection services like API or MUA inspections. We are active in the piping inspection business with different kinds of services: short range, mid range, long range UT, but also we have the MFL head scanner, pipe scanner, and Ronald will talk later on a little bit more about the mid-range UT. We're active on pressure vessels, on pipelines with the DCVG SIP service, with a large standoff magnetometry, and the NIPA service, where Louis will focus on later. And we also have the cold tubing inspection services by means of our ACAM tool. Some key facts. So in total, we are performing around or more than 4,500 inspection services on tanks, pipings, and pressure vessels every year, of which more than 1,200 are tank inspections and more than 500 are tank bottom inspections with our T-Bit Ultra tool. And about that tool, I will talk now a little bit more in detail. So I've split my presentation in 3 chapters. So I will start with talking about what is the T-Bit Ultra. Then I will present a couple of benefits of the high-resolution MFL data we generate with the tool. And in the end, I will talk about the service specifications. So what is the T-Bit Ultra? The T-Bit Ultra is the latest generation of our tank floor scanner. And when I say latest generation, we are looking at a history of more than 30 years of experience and development. So the first tool was developed in the 1990s. And since then, we had a couple of revisions, and the latest version is now the TBIT Ultra. What we did there mainly is we took the sensors that we use also on our inline inspection tools and put them also on the TBIT tool to increase the resolution mainly, but also to benefit from data evaluations and algorithms and the experience we made also in millions of inspection of pipeline kilometers. So as mentioned already, the main change of the latest versions, the new generation compared to the previous generation, is the amount of sensor channels that we use. So the previous tool version had an amount of 154 sensor channels, whereas the new version has more than 1,000 channels. And with this, we could realize almost 7 times higher resolution. The old tool had a sensor spacing of around 6 millimeter, whereas the new tool has a sensor spacing of 1.6 millimeter, and by that we could of course significantly increase the tool sensitivity and precision. So what are the benefits of the high resolution MFL data? Obviously, the higher sensitivity allows for an earlier detection of smaller defects. I will come to that also later, what the detection threshold and sizing accuracies are. But also by using technology which has been validated and proven on the inline inspection side, we could also piggyback on the analysis and also use very stable and safe algorithms for feature evaluation. So talking about feature sizing, but also talking about the determination and disabling of potential false calls. By an automatic feature detection and sizing, so our tool detects and sizes features on the fly while we are driving over the plates. We are immediately seeing the results on the laptop screen. We are reducing hours in confined space, and in the end, of course, also out of service time of your asset. And the results can be used for RBI assessment, and in the end, by a very accurate determination of metal loss, we can also increase inspection intervals and next inspection dates. So if we look at the signal interpretation, so how we as ROSEN do interpret basically our MFL data. I mean, we also record eddy current data, but this is mainly for lift-off measurements. We are not only looking at the signal amplitude. Many scanners on the market, they purely look at the signal amplitude and use that for feature detection and follow the indication up with another follow-up method. However, we look much more deeper to an MFL signal and not only look at the amplitude strength. Of course, we consider that as well, but also look at the steepness of an amplitude, the shape, the neighboring sensors, the length-width ratio, and so on and so forth. There are hundreds of parameters that we look at, and with that, we can pretty accurately determine how big also an indication is, because the screenshot or the picture on the right side shows that pretty small defects, so like 5 millimeter in diameter, can be pretty deep, and these defects have a pretty small amplitude and wouldn't be detected by an amplitude-based threshold. So medium-sized defect, for example, 15 millimeter in diameter, 50% metal loss, could be detected with an amplitude-based threshold, depending where we set it, but only the big ones are reliably detected with the amplitude-based threshold. And with a signal-based threshold, all of these 3 indications are detected. So the more shallow ones, which from an integrity point of view, probably not critical, but also the small ones and deep ones are reliably detected with a signal-based approach. How is it important? Why is it important to make an accurate feature determination in point of detection, but also to accurately size an indication? Because with an accurate feature size, you can in the end extend your next inspection date. How does it work? So in the tank, we typically have a nominal wall thickness. To be safe during the following operation, an operator typically has a safety margin or repair threshold. Above that is the degradation allowance. So that's what we allow the bottom to corrode. And of course, we want to have still the safety margin or the failure zone in place when we inspect it the next time. based on our readings, our MFL data, we calculate a degradation rate. And as more accurate our MFL data and our feature depth is, as more accurate we can determine the degradation rate, and as more accurate we can determine the next inspection date and also the remaining life of our asset. So by more accurate measurements, we can extend the asset lifetime and lower the probability of a failure. So here's a small example. So let's so new tanks are commonly inspected after 10 years in commission. Normally there's only limited corrosion present at the time, and the next inspection dates derived from this inspection often do not reach allowable limits. So if you have extremely low detection and repair thresholds, that would be needed in order to actually achieve a calculated inspection interval of 20 years or greater. So for example, if we take a floor scanner B and have a tank which was constructed in 2010, inspected in 2020, has a nominal wall thickness of 6 millimeter and a typical detection threshold of 20%, that would lead to a next inspection in 10 years. If we now take the T-bit Ultra as example, and just by lowering the detection threshold from 20 to 10%, we can, and also of course, consequently repair them from 10%, we come to a calculated next inspection of 25 years. However, API 653 up to now maxes it to 20 years. Nevertheless, this is the next inspection interval could be doubled just by going from a 20% detection threshold and repair threshold to a 10% limit. However, if you go to that low detection threshold, you also get more indications, obviously. And here I have an example of a tank that was inspected in several modes. Yeah, we also have several scan modes that we offer, but I will come to that also in a second. Actually, there was a 60-meter tank. Inspection duration was 3 days, so that was the scanning time that we needed to scan the surface. Actually, the defects found in standard mode, so reporting from 20%, was around 15,000. And if we look at the detection threshold of 10%, we came up with almost 400,000 indications. The data evaluation time took 0 seconds, so as it is done on the fly. And if we look again to other systems on the market, which are working on detection only and consider only the standard reporting threshold of 20%, and the need to follow each and every indication up, so we just calculated 3 minutes, so we end up with 750 hours of additional time, or 75 man days for follow-up inspection. So is this cost and time taken, and what if it isn't? So that's of course an important question. The other thing is, there's of course critical areas in a tank, especially next to the corner weld. We have the critical zone, critical areas, and there it is important that the scanner has almost no blind zone. And here we have an example where we, with the T-bit Ultra, scanned an annular plate next to the shell course, and the tool found an indication, as you can see in the line plot as well in the C-scan. The tool sized the indication as 96% deep. Actually, after the removal of the epoxy coating, it was confirmed that there was even a hole. So actually, this shows that the tool can also detect and size defects close to the corner weld very accurately. So as mentioned earlier, with the T-bit Ultra, we rolled out 3 different service levels. Actually, we call them extended, standard, and essential. And they are differentiating between each other mainly by the detection threshold, but also by the deliverables in ROSEN for tanks. The extended service level reports from 10% and has almost or has every functions that we can offer in ROSEN, including a lift-off and a coating thickness map, as well as a wall thickness map. The standard service reports from 20% and has also quite some features in ROSEN, including feature statistics, feature lists, and of course the stripes and features above 20%. The essential service reports just the bare minimum as we see it, so from 40% metal loss and 10 millimeter in diameter, and just includes the form maps and the stripe view. All services can work up to 6 millimeter for feature sizing, and up to 10 millimeter for feature detection. Maximum blade thickness is up to 16 millimeter. And yeah, the number of sensors I mentioned already, we have more than 1,000 sensors on the tool, MFL plus eddy current. Internal external discrimination is possible, so the tool can reliably say if the indication is top side or bottom side, which is crucial for the determination of the repair method later on. And we reach a scan speed of around 100 square meter per hour. So with our tool, we are actually able to, we call it, to find the needle in the haystack. So the reliability of the tool is by far exceeding conventional MFL or eddy current scanners. Indications from 2 millimeter in diameter and 10% metal loss can detected, and size up to plus minus 4% in accuracy. So also the sizing accuracy is by far exceeding manual UT. The inspection turnaround is faster due to automated feature detection and sizing. And yeah, the whole inspection is possible for coating thicknesses up to 6 millimeter, and the coating does not need to be removed for inspection. Yeah, actually, that was my part of the presentation, and I would be happy to take some questions.
Yeah, thanks, Richard. A very impressive story. Can you say something about the typical customer feedback that you get?
Yeah, so yeah, of course. So customers are typically very impressed by the tool's sensitivity. So as you could see in one of the earlier screenshots, so we are picking up a lot of stuff. As with the 10%, we are close to the noise level, and as you can imagine, we also pick up a lot of false calls, and therefore also the automation in the process. So the algorithm development was a key part of the development of the T-Bit Ultra, because we knew that there was such a high sensitivity, we'll pick up all kinds of stuff, and so therefore it is also highly important that we also determine what is the true call and what is the false call. And this reliability plus the sensitivity, that is typically feedback where customers are pretty impressed about.
Yeah, excellent. There's quite a specific question here. Let me read it out. Is it real to use multi-tool instead of MFT and TFI tools? If no, then why?
Well, so I don't know if so a multi-tool. So can you repeat the question maybe once?
So is it real to use multi-tool instead of MFT and TFI tools? If no, then why? It's perhaps a little bit cryptic. The person asked the question. Perhaps you can clarify a little bit further what you're looking for, and then we'll answer it at the end of the session.
Yeah.
So that's one other question, and then we'll go to the next presenter. Very impressive TBIT Ultra tool. Is it available to purchase or rent from ROSEN?
No, actually, we as ROSEN are a service provider. So it's currently not possible to rent a tool or to purchase a tool. You can just, at the moment, hire ROSEN for an inspection, and we come with a team, including the equipment, and perform the tank bottom inspection and the end deliver the report. So that's currently our service concept.
Thanks, clear. Let's move to the next presentation. But if you have any other questions for Richard, please type them in the Q&A box, and we'll do a Q&A session at the end. But for now, let's continue with Ronald's presentation.
Okay. Good morning, everyone. For some of you, good afternoon. My name is Ronald Tulst. I'm a business line manager at ROSEN, and I'm located in Rotterdam. In the next few minutes, I'm going to talk about corrosion under pipe support, the cups, and which technology ROSEN has available for this mechanism. I'm going to talk about what the IMAT-IFSE is, a little bit about the technology, the way we apply it. I'm going to share some experience with a customer, experience with field tests, and I'm going to explain more about the service specification, what the tool can do and what the tool cannot do. Looking first at what is it built for and what are we using it for. What is in principle IMAT-IFSE? IMAT-IFSE is an inspection technology specially designed for inspection at non-accessible areas. We know the IMAT technology already for years in the inline business, but ROSEN has developed a handheld device for measuring corrosion at pipe supports for pipes that are in service and we can screen the corrosion, but also size the corrosion in percentage metal loss. Typical example, for instance, are in the next photos, where you can see, for instance, what kind of mechanism we are looking for. Here you see the touch point corrosion at the 6 o'clock position. Often crevice corrosion can occur, but we can see something is happening, but we cannot see how deep it is, how far it goes. Also, the accessibility can be sometimes a challenge, and this is why we have developed also our EMOT-IFSA system. Next, Richard. Thanks. Thank you. For those persons who do not know what EMOT is, I want to explain it in the next few slides. Perhaps you know EMOT-IFSA in the past from wall thickness measurements. EMOT is often used for ultrasonic wall thickness measurement at high temperatures. What is the difference between EMOT and ultrasonic? I think everybody knows traditional ultrasonic using a piezoelectric transducer with crystals creating the sound, a couplant getting the sound in the material, and then you can make a wall thickness measurement. EMOT is also ultrasonics, but the way the sound is created is different. The sound is created using a magnet in combination with eddy current coils. This way, we introduce the sound in the material itself. So it has some good advantages. No couplant is required, and that also means there's a non-contact method. It is less sensitive to service conditions. And this is very helpful, of course, when you look at the service conditions of pipes. It's often not the best condition, but for the EMOT, it doesn't matter that much because, as I said, the sound is generated in the material itself. The EMOT itself is not new. It's already existing a long time. But the way we apply EMOT at ROSEN is different. We have a sensor and a receiver. And instead of making a wall thickness measurement, we create the sound in such a way it travels through the pipe wall. And that's very attractive because that means we can put a sender at a location and a receiver at a location, and we can measure in between. That's why the system is very unique and it can travel and measure corrosion at a distance of around about 70 centimeters. Next one. This is the way the tool looks like. So here we have the tool. Let's first talk about the picture on the right. Here you see a sender and receiver at the 1 o'clock and 11 o'clock position. The sound is generated by the sender and pumps from the top side as well as from the bottom side. So we cover 360 degrees, the sound. When you look at the top side, we call it the short path because the distance it travels is shorter. The other one is the long path. And the interesting part again is that you see we send out a signal and we receive a signal, and it travels over the 6 o'clock position, exactly the point where we have an interest of corrosion, but you want to measure. That means the tool itself, you have to move in the axial direction. So you drive over the support, measuring the 6 o'clock position. This is in a very big nutshell how the EMOT-IFSA system is working. But I will go a bit more details in the next few slides. How the signal looks like, I will not go into too much detail, but it looks like the blue picture that you see here on the right side of the screen. We see here the short path, the long path, and we see disturbances of the sound, meaning with an algorithm, we can calculate the amount of metal loss. Normally, we scan every support twice to ensure the repeatability of the sound is good. Since a measurement is taking only 1 minute, or perhaps even less, it's easy to make 2 measurements and we confirm then we have the correct wall thickness and the correct metal loss. Looking at the table on the right side below, you see the scan number, the pipe number, the support number, the file where we store the raw data, but also exactly the amount of metal loss that we have measured in percentage metal loss with a statement on the quality. For each and every support, we provide you with the information of the amount of metal loss. In the summary, we have a similar reporting as we do also with the floor scanners that Richard just discussed, where we have then the different types of metal loss, but also if the quality of the data is less, that can be, we can still do a screening, and then we have a qualitative assessment. When we do the qualitative assessment, we can still provide information on the screening if follow-up is required or not. And this is then how the system looks like in the field itself. You see we have for different pipe diameters, we have different sensors, and it's a very hands-on system. You put the system on top of the pipe. In this case, you see on the picture on the right side below, it can also measure when there are some obstacles, as long as the top side of the pipe is accessible. The pipe doesn't have to be cleaned. This is sufficient because, as I said in the beginning, the sound is created in the material. So it, of course, coating may have some influence when it goes very thick, but in generally paintings are no problem. Next one. Just an example of a large project we recently completed. We recently completed for a large facility in Europe. They inspected all the support of this facility, more than 10,000. We used some statistics on how the system functioned. We calculated that we have on average 25 supports per day. That's including bad weather, including standby, including difficult lines, including easy lines, but on the average 25 supports per day. On a good day, we reach even 60 supports per day. So the measurement is fast, and of course, time is money, as we all know. The type of supports that we inspected are ranging between 4-inch and 24-inch, but predominantly the supports we inspected were 10 and 12-inch. For this customer, we calculated the length of 65 kilometers, so we did quite some walking along the pipelines. Out of all the 10,000 supports we calculated, we have seen that 80% of all supports we could inspect with the EMOD IFSEN. Looking at the results for this specific customer, we found 260 supports which we recommended for repair and 350 supports that we recommend for follow-up. So for this specific customer, I do not know how many, but I'm pretty sure we have prevented a lot of problems and leaks upcoming in the future. We also do some testing itself. We have some lab testing and extensive testing in Lingen in Germany at our facility. We also have performed HOYS trials, and for those persons, those companies member of HOYS, you can receive the results request them at HOYS. Of course, we also did some other validations and compared our results often with other traditional methods, but then you have to remove the support. If you look at the diagram on the right side of the slide, there you can see the real corrosion versus the measured corrosion. Of course, ideally, it should be on the red line, but what you can see is that commonly we have a spread of about 15%. What's also interesting in this diagram is that we can size features, the smaller ones, but also the ones above 50%, which we can also size in percentage metal loss. Next. Looking at the specification of the tool. The specification, of course, is available, which you can also see on our website. Just a short summary. We are talking here about the phenomenon of thinning at pipe supports, meaning a detection threshold of 15%. Commonly, our specification for sizing the corrosion is plus minus also 15%. The tool can size for pipes from 4 to 14 inch, up to a wall thickness of 10 millimeter. If the wall thickness becomes more than 10 but less than 15, we can still inspect it, but then we can only screen, and we need a follow-up method. When the tool is more than 14%, we can only do screening, and we have to do also a follow-up measurements. As I said before, coating thickness up to 500 mil is possible, and commonly we inspect, in this case, 25 to 50, 60 supports a day. Then I will come to the summary. Some key advantages of this technology. This technology is designed to inspect non-accessible areas. Cups often have non-accessible areas. It has an automatic sizing for corrosion at pipe supports. We always scan it twice. We have algorithms, and it is operator independent. We have the technology suitable for multi-pipe diameters and type of supports. Often, in most cases, no surface preparation is required, no coating removal. It goes very fast, and that's also, of course, time saving and accurate. The raw data is always stored. That means if we do, for instance, 6 years later, again inspection, we compare the data from now to the one from in 6 years. It also has easy and clear reporting, and as I have just shown you. Of course, we can also combine this technology with other technologies, like for instance, short-range UT or other technologies, if that would be needed. This is my presentation. Are there any questions?
Thank you, Ronald. A very impressive story. There's a specific question. Let me read out. It appears that with this tool, you get an overall metal loss percentage at the support point. But is it also possible to get a specific accelerated corrosion metal loss? For example, can the equipment reflect a specific point where the thickness loss is very high compared to the average loss?
If you want to focus the metal loss on a specific area, we have also other technologies, like for instance, short-range UT, to look in detail where the corrosion is located. So we have to use then a combination of other technologies, but in principle, when we look at the cups, and in this case, the touch point, commonly that's the point of corrosion. And if there would be corrosion on other areas, there are also other methods that we have available, but these will not be discussed in this webinar.
Yeah, excellent. Hey, and it's very impressive to see what this technology can already do. Are there still, say, some areas where you're still working on further R&D to further advance the tool? What are, say, what's still on your wish list, so to speak?
Of course, we always have a wish list, and always there's room for improvement. There are some limitations to the tool. For instance, when there are clamps. When there are clamps, the tool cannot pass it. So that means you either have to remove the top side of the clamp, then the tool can pass, or you have to go for another technology. And especially, of course, the lower part of the clamp is of interest because that part you cannot remove. And there we have also additional technologies available, which are based on phased array. And this is also the technology development that we are now introducing in the near future.
Excellent. Thanks, Ronald. A very impressive story. Let's move on to the final presentation. Let's go to Lewis.
Brilliant. Thank you, Eric. Hello, everyone. I'll introduce myself. My name's Lewis. I'm based in our UK office, and I'm the service manager for our above ground survey solutions or above ground inspection solutions. The presentation which we'll talk about today is about our non-intrusive pipeline assessment. We'll go into a bit of details as to what it is and how we use it. And it's the culmination, let's say, of not only the inspection, so the NDT or anything above ground that we're doing, it's actually the combination of inspections with integrity. Before I was a service manager for this service, I actually spent 10 years of my time in the integrity world doing assessments and analyses of pipelines to understand how long the pipelines were going to last, estimated remaining lives, and when things would have to be repaired or what improvements could we make. So taking that knowledge of myself, we've brought that in-house and we've created the non-intrusive pipeline assessment. What is it? It's the NIPA for short, as I say, primarily an above ground integrity analysis approach, and primarily we're looking at challenging or unpickable pipelines. So pipelines which, from the ROSEN perspective, we can't get an inline inspection tool into easily. Therefore, we need another method of being able to assess them. We incorporate our above ground surveys with our engineering experience into a direct assessment methodology, which is guided by the NACE and other international standards. So NACE SB 502, for instance, for external corrosion defects, 204 for stress corrosion cracking, and 206, 8, 10, and 16 for the internal defects. There's also the new standard, ISO 22974, which is the pipeline integrity assessment approach standard. So everything that we're doing is combining all of these standards together. The key thing with us is essentially we provide that rigorous, structured, and crucially industry-recognized approach to evaluate integrity of a pipeline system. And our key difference is the addition of large standoff magnetometry, which we'll very briefly talk about in this presentation, and now our machine learning models, and how we're using those machine learning models to enhance our NDT. So the combination of above ground or inline inspection still sets the standard for quality inspection data. So ultimately, if you want the 100% coverage of your pipeline to understand every defect that's in there, ILI is still setting the standard for that. And we're certainly not trying to replace it in any way. However, as I said before, not all pipelines are piggable. Some of them can't be pigged for a variety of reasons. It could be physical restrictions. It could be there's requirements for flow within that pipeline that have to be met, for instance. So this approach is a way of giving us an understanding of that pipeline condition without having to stick anything inside the pipeline. By combining the above ground inspections, so combining, for instance, our cathodic protection surveys with our large standoff magnetometry, we increase the confidence in the results, and that can all be obtained without inline inspections. So some of the inspections that we conduct are SIPs, DCVG, ACVG, or CAT testing for our cathodic protection surveys. We also have our geospatial and technical surveys. So, for instance, we can perform LiDAR, photogrammetry, ground resistance, strata analysis, etc. Large standoff magnetometry, as I mentioned before, which we're using to find stress indications, stressed areas within the pipeline, and our AI machine learning and data analytics programs with virtual ILI. Now, non-intrusive pipeline assessment essentially just means the combination of any of these data sets together to allow us to get more confidence and a better understanding of what's going on. An easy example is, for instance, if you only perform a close interval survey, that will give you an indication of how good the cathodic protection is on your pipeline, but it won't give you any idea about the size of any potential wall loss defects which may be there. By combining close interval surveys with coating surveys and large standoff magnetometry, not only can we tell you what the current cathodic protection status is of the pipeline, where coating defects exist, but with the additional layer, we can also then analyze, do you have coating defects which correspond to stress raises, which would indicate you have potential wall loss, or do you, for instance, have defects or coating defects, but the cathodic protection system is doing its job and it is stopping any corrosion occurring because we're not seeing those stress raises. By combining that with our AI machine learning models, we can also compare it to our database of inline inspection data, which we'll talk about very, very shortly. But essentially, to summarize, the approach of overlaying data with the NIPR analysis is a cost-effective way to reduce the number of excavations that we need to conduct, and also monitor existing defects for change, so we can lower the costs of inspection and also increase the safety. We can perform monitoring in between inline inspection, so we can increase data availability and resolution. It's obviously a very big undertaking to put a pig in a pipeline, so being able to inspect discrete sections of concern is a massive benefit to our clients. We can increase asset utilization. As I mentioned before, it's completely non-intrusive. We don't have to upset any of the pipeline flow. We can do this while the pipeline's operational. And we can screen and prioritize pipelines either for inline inspection or for estimated remaining life. So we're only inspecting when it's needed. A classic example, for instance, is many clients may come to us with a number of pipelines which they don't know the criticality of. We could perform non-intrusive pipeline assessment to understand which of those pipelines should be picked first and which ones can be picked at a later date. The non-intrusive pipeline assessment, we're using our AI machine learning. So we're taking the knowledge that we have from our inline inspection business, so exactly what Richard and Ronald just said, taking the sensor technology and the algorithms, for instance, from inline inspection. What we're interested in is what the results of those inline inspections were. ROSEN have a vast database of inline inspection runs, over 26,000 runs over the past 30 or 40 years, and with over 1 billion registered anomalies inside. So can we take all of the data from these inspected pipelines and use this to give us an understanding of our uninspected pipeline? Could this be something like virtual inline inspection? Can I look for commonalities between those and work out which or what size of a defect I'm going to find in a particular location on my pipeline versus the other? And this is just a brief summary of the size of the asset, or the integrity data warehouse, as we call it. Millions of joints from thousands of pipelines, as I said before, over 26,000 inspection runs. We have billions of metal loss anomalies in there from over, well, multiple millions of kilometers of inspected distance. So again, within that data set, we can look for commonalities between our uninspected pipeline and the inspected database. By taking the holistic approach, which is reliant on the data layers, we can increase the confidence, as I mentioned before. And by doing this, it makes the overall process more accurate and repeatable, also more reliable. Every non-intrusive inspection method, regardless of what it is, be that close interval surveys, DCVG, ultrasonics, even inline inspection, has limitations, but understanding those limitations and being able to put measures in place to counteract them or mitigate them is what the key thing is. By overlaying the different data sets, we offset any weaknesses in that data. The more layers that we have, the less effect these limitations have. And for those of us that are in the integrity world, we can remember the classic Swiss cheese model, or ROSEN Swiss cheese. The more layers that we have, the less likely we are for those unidentified defects to actually get through all of the measures that we've put in place. If you click again, Richard. So what does all this data look like? Essentially, this is a demonstration of the multiple data sets that you can get off of a non-intrusive pipeline assessment in combination with large standard magnetometry. Locations are deduced from the inspection assessments, so SIPs, DCVG, and LSM in this case, and we overlay all of that data within an algorithm to understand the commonality of defects and also provide justification on why we picked a particular defect versus another. So for instance, if we look at the graph here, we can see the square boxes in green and yellow. If we only consider DCVG, which is what these boxes represent, you may, for instance, only investigate the singular defect at around about the 7-kilometer mark, where you have the largest coating defect. Anybody who's used to analyzing DCVG data and doing corresponding coating repairs will know the frustration of excavating a very large DCVG defect and finding no corresponding corrosion because the CP system is doing its job. Likewise, if we look at the LSM data, which is represented by the gray dots in the blue dots on the screen, again, there's no clear outlier in the data, so only performing LSM inspection, although this provides us with lots of useful data, you may have to then look at performing inspection at each of the high points along that pipeline. And along the top row there's around about 15 locations, for instance, that you may have to go and inspect. So only looking at single data sets can lead us down multiple different paths, and obviously one may be a lot less, but may not give us any useful information, whereas the other one may be too conservative or too excessive. So if we click this again there, Richard, as I mentioned there, yeah. So by combining all of these data, we turn that graph into the following. The severity rank, as we call it, which is essentially a ranking method taking into account all of the corresponding factors from the multiple inspections that we've conducted. And this reduces the number of excavations and provides justification for that. So, for instance, from before, only considering single data sets, we may have only inspected one location, whereas by combining data sets together, we can reduce that, or we can increase or reduce that number depending upon the requirement for the pipeline. We provide also a severity baseline. So this is for low-level indications. So as I mentioned earlier, the main thing with NIPA is the repeatability. So by performing a baseline inspection and getting this following graph, the next time that we actually perform these inspections, we can compare the differences, and we can actually look for the relative change in defects. And rather than looking at the absolute numbers, we may actually become more interested in the defects which have changed more rapidly with time. And we can present that data in many ways. For instance, we have the XY plot here, where you've got distance or running distance along the bottom versus the overall severity ranking. And if Richard can just one more time for me, that should give us a GIS output. So for instance, multiple different ways that we can report this. All of the locations and inspection types that we use are GPS logged. So again, overlaying this data into GIS to then take it to the next level and also implement it in existing systems is one of the key things. We go to the next slide. Yes, and that's the end, as I thought. So Eric, thank you. Back to you.
Yes, thanks for that presentation. Hey, one question about the machine learning. Is it indeed the case that with all the data that you have and with the machine learning capability, that you can then better prepare for upcoming inspection jobs and know where to look at, so to speak?
Exactly, and that's exactly how we're using it. We can use it in combination with the non-intrusive pipeline assessment to provide extra confidence. So for instance, a classic case study that we have is we inspected a pipeline and we didn't find any significant defects along its entire length. The main problem then becomes is, did the above ground surveys perform the task that they were asked to? Are there actually no defects there, or have they just failed in some kind of way? So you have that unknown aspect brought into the mix. The machine learning, however, we can use that as an independent source to then say, okay, well, based on the input parameters, this pipeline, how does that compare to the thousands of other pipelines that we have in our database? So by looking at the commonality between them, finding pipelines with the same coding type, operational parameters, location, field use, for instance, that it traveled through, what did those pipelines tell us? And they also showed us that, yes, there were defects, but relatively small defects. You know, the maximum defect size that we would expect is up to 25% based on a probability of 0.8. So we knew that then that we had good data from the above ground surveys because we were backed up by the virtual inline inspection. And then when we actually did excavate the pipeline at some of the hotspot locations where we found those indications from the above ground surveys, we found corrosion defects of around 11 to 15% of the wall thickness. So right in the middle of the predictions of the virtual inline inspection, but also giving us the confidence that the above ground inspections, the indirect ones, actually did their job properly.
Yeah, excellent. If anyone in the audience has some further questions for one of the three presenters, please type them in the Q&A box. As we wait for some more questions coming in, let me also reflect a little bit on what we used to do in the Shell days before starting technologycatalog.com. In my last job at Shell, I was leading a global technology task force in support of producing assets around the globe. It was part of the Global Production Excellence Organization. Production Excellence had 6 improvement themes for maintenance, reliability, turnarounds, and 3 others. And for all those themes, we had a technology program in place. I can just say that all the themes that were addressed during this webinar today were hot topics in those days. And it's really impressive to see and to listen to all the progress that has been made over the past year. So really great to hear. So thanks for the presentations. I see a question coming in for Ronald. Are there any temperature constraints, Ronald, for the solution that you presented?
Yes, there are temperature constraints. It also depends, of course, on the time that you spend the tool on the pipe. The longer the temperature, the tool is in touch with temperature, the less hot it can be. But in principle, the current technology can go up to 100 degrees centigrade, but we have to avoid long time exposure to the temperature of the pipe. And besides, for the minimum temperature, we normally go for ambient, so above 0. Although the technology can also work, I think, below -10, but commonly we prefer to work above 0 to a maximum of 100 degrees.
Yeah, excellent. I think there are no more. Oh, there are. Yeah. Let me see. So there's a question for the pipe support. What do you do if EMOT cannot be applied at a support, for instance, at clamp support?
Yes, the clamps is still difficult because you can have corrosion all over the 360 degrees. But of course, yeah, we say then, for instance, remove the top side of the clamp if that's possible, or remove the clamp so you have access. But that may also not always be possible. So we also have other techniques, and we're also developing new techniques, like for instance, phased array technology. We currently are using short range UT, meaning a high frequency phased array, where we can scan 360 degrees on the clamp. But then you have to clean the clamp where you put the sensor to, and then you can scan with a short range UT round about 10 centimeter.
Yeah, excellent. And another question coming in: can you use the EMET IFSC technology also to detect internal corrosion in the pipe?
Yes, it detects internal as well as external corrosion. Although the tool itself predominantly focuses on the cups, on the external corrosion and the crevice corrosion. If you have a pipeline where you expect internal corrosion, you could use also the EMOT ISO for screening, but we also have a combination with other tools like an MFL pipe scanner that we commonly use for the internal corrosion. So we're looking at the damage mechanism, and if we have access, we take the MFL scanner. If we don't have access, we use the EMOT ISO, but we have possibilities also, of course, to find the internal corrosion.
Yeah, excellent. And a question to Richard. And in one of the last slides, the internal/external classification was mentioned with yes in the tool specification. But how good is the quality of the internal/external classification?
Yeah, I mean the internal-external classification is a crucial part for the feature sizing to get it correct. Because we, next to the two other parameters, we of course look at the amplitude of an indication, and you can imagine that an internal indication has of the same size of an external indication have different amplitudes. So therefore, it is crucial to get correct if the defect is on the internal or on the external side of the plate. We specify a correctness of more than 90% in the field. However, on our calibration plates that we have here in the workshop, we get it also 99% accurate, also on the smallest defects. But in the field, we specify a correctness up to 90%.
Yeah, excellent. I think that covered all the questions. So thank you very much for all the presentations. I'll use the remaining couple of minutes to give a brief update about the platform. But before I start sharing my screen, many thanks to the host presenters today for these insightful presentations. Very impressive. So thank you very much. And let me start sharing my screen. So I need to do a few things to make myself the presenter. And all the ROSEN presenters are still able to talk. I'll give a closing remark at the end, but let me share my screen for a moment. So if correct, you'll see the homepage of technologycatalog.com coming up, something that most of you are probably familiar with. So the platform, and that's one thing I want to highlight, already contains over 2,300 solutions. You can access them via the menu. That's one way of doing that. Another thing that we do is that we now also have an AI companion, AI assistant, that can be accessed by, for those that have the right subscription with us, by going to the toolbox environment, your own toolbox environment, and then click on Ask Steve. Steve is our AI companion. And by typing a question and asking a question to Steve, Steve will then find the right solution for your challenge. So if you're not yet familiar with this functionality and would like to give it a try, please contact us and we're happy to provide background. And if you're not yet a subscribed customer, we can also make it available as part of a trial. And the final thing I would like to highlight is the growing number of challenges on the platform. We grow the content of our platform based on the challenges of our customers. If I go to the menu at the top, there are the challenges. These are the ones that are currently live. It's a growing list. Some companies post a challenge by company name. You see some examples there, like Shell, Aramco, and KNPC, and others. Some others do it in an anonymous way, but whatever way is chosen, as a supplier, you can respond to the challenge. And that way, getting in direct contact with the challenge owner and have the dialogue with them. And we do see that for the companies using this challenge feature, they like it because they get access to the right solutions. And obviously for suppliers, it's a great way to get in contact with potential customers. So if you haven't had a look at the latest challenges recently, please go to the website and go to challenges in the menu bar, and you'll find the latest challenges. So those are the key things I want to highlight. So with that, would like to end here, unless there are any final closing remarks from one of the ROSEN presenters. Any closing remarks, Richard, Ronald, or Louis?
Just thank you for this opportunity, Eric, to be able to present this. So thank you very much.
Most welcome, and it was again great to listen to the stories. And for those attending today, there will be another webinar. Please stay tuned. You'll be informed by having an account at technologycatalog.com. This way, receiving our newsletters. We also announce the webinars via social media, and so we look forward to seeing you in one of the next webinars. So thank you very much, and have a great rest of the day or a great evening. Thank you.